Hello again. In the previous lesson, we solved exponential and logarithmic equations. In this lesson, we're going to apply those ideas to real situations. And we will work with exponential growth, exponential decay, half-life, solving for time, and continuous compounding. So let's begin with the quick rules. Here we have the model for exponential growth. We have the exponential growth decay model as well. And then we have continuously compounding growth modeled here. And then we're going to use logarithms to solve for time in exponential models. All right. So example number one, a population starts at 2,500 and grows by 6% per year. Write AT, find A where T is 8, and interpret the growth factor. Okay. So again, this is an exponential growth model because the population is increasing by a percentage each year. Okay. So it's growing. Oh, so it's growing by this amount every year. So this is an exponential equation model. So we're going to use A parentheses T equals A sub O 1 plus R raised to the power of T. Okay. So the initial amount is 2,500. So A sub O is the initial amount, right? So the initial, okay, initial amount is A sub O. Okay. Make sure that's clear for you. So A sub O, which is the initial amount is 2,500. The growth rate is 6%. So as a decimal, 6% is, so the decimal is always on the right hand side of the whole number. So you're going to move the decimal two spaces. So if we have this number 6, we're going to move it 1, 2 right here. That's going to be the new location. So it would be written as 0.06. Okay. Or you can write just decimal point 6 either way. Okay. Now we're going to substitute into the growth model. So this is the growth model here. We're going to substitute the information that we currently have. So we have A sub T, or excuse me, A parentheses T equals 2,500 multiplied by 1 plus 0.06 raised to the power of T. This simplifies to 2,500, 1.06 raised to the power of T. Now we need to find A where T is 8. So using, we can essentially use a calculator to approximate this. So if we substitute 8 into the equation, remember we're just replacing the T with the 8, we would get an approximation of 3,984.6. So since this is a population, we can round it to about 3,985, right? Because you can't have a percentage of people. So the answer to this problem would be A is approximately 3,985 people. Okay. Now, interpreting this growth factor, the growth factor is here. So 1.06. What that means is that each year the population is basically multiplied by 1.06. So in other words, the population keeps its 100%, or excuse me, keeps 100% of what it already had and then gains an additional 6% each year. So whatever that amount was, it gains 6% each year. Whatever the new amount is, it gains another 6% from that. And then whatever the new amount is, year 3, it gains a 6% um, growth rate from there. Okay. So those are the initial factors. So growth factor is 1.06. The growth rate is 6%. And the interpretation is um, that we multiply by 1.06 each year. Okay, let's continue. Example number 6, or excuse me, example number 2. So we're dealing with the decay model. So the first model was a growth model. Now let's look at a decay model. Um, Unfortunately, in America, a car depreciates as soon as you drive it off the lot. A car is worth $28,000 and it loses 12% of its value each year. Write VT and estimate the value after 5 years. Okay, so this is a decay problem. So we know the function for the decay. So we're going to use v in this case. V is a function of t equals the decay model is a sub o parentheses 1 minus r parentheses raised to the power of t. So in this case, we're going to use the v and we're going to say 1 minus r raised to the power of. The initial value is here. Okay, so this is the initial value of it, and then this is it loses 12%, so that would be the decay. Okay, so um, the initial, right, is represented by AO, or in this case VO, and then the depreciation is loses that much. So I'm just going to go ahead and substitute that information into what we have, and remember 12%. If you take 12%, that decimal is here. When you move it over, going to be 0.12. Okay, so using that information that we have, VT equals the initial, which is 28,000, parentheses 1 minus the interest that it loses, excuse me, the percentage that it loses, that's 0.12 raised to the power of t. When we subtract this amount from this, we end up with 28,000 multiplied by 0.8 raised to the power of t. Okay. Now the decay factor is 0.88. So that means that the car keeps 88% of its value each year. Okay. So it's not gonna retain this, but it's gonna keep 88% of its value each year. Now estimate the value after 5 years, right? We're gonna estimate the value after 5 years. So that means all you do is substitute the 5 to the decay formula. T stands for time. Doing that, you're going to end up with B5 approximately 14,776.49. Okay. So after 5 years, the car's value or the car is going to be worth 14,776.49. Okay. So the important idea is that the car does not lose the same dollar amount each year. That's the most important thing, right? The car is worth 28,000, loses this amount of its value each year, and then so and estimate the value after 5 years. So again, um, the important idea is that the car does not lose the same dollar amount each year. It loses 12% of its current value each year. That's important. Okay. All right, let's continue. Pause and try this. Okay, so the model is given, excuse me, the model is already given in the correct half-life form, right? What we need to do after reading this, a substance begins with 80 grams and has half-life of 12 hours. Write a model using AT equals 80 times a half raised to the power of T divided by a half. Then find um, the uh, the half-life at 36 hours. Okay. So first of all, the 80 is the starting amount, right? The 80 is the starting amount. That's important. Okay. And the 12 is the, excuse me, the 12 in the exponent, right, up here, means the half-life is 12 hours. Okay. So this T divided by 12, right? That means um the half-life is 12 hours. Okay? That's important. And then the 80 in this case is the start amount. Okay? So we would say it's already in its proper form here because this is A sub O, then multiplied by a half raised to this. Okay? Now, all we need to do is essentially substitute the 36 into this formula. So we have A sub T equals 80 parentheses 1 half raised to the power of T over 12. Okay. Now, substituting the 36 in there, we're going to set this equal to 80 times a half. And then it's going to be raised. Now, keep in mind, so 36, right? So it'll be 36 over 12. And that simplifies to 80 times 1 half divided by, I mean, excuse me, 36 divided by 12 is going to be 3. Okay. And then we can calculate it. So, first of all, a half raised to the power of 3 is essentially 1 half times 1 half times 1 half. So, 1 half raised to the power of 3 is 1 half, 1 half, 1 half, and that equals 1/8, right? So this is 1/8. Okay. So that's essentially coming back over here. A to the A at 36 is going to be 1, or excuse me, 80 times 1/8. 80 times 1/8 is going to be 10, right? Because 80 times 1 is 80. 80 divided by 8 is 10. Now, what does that mean? 10 grams would be the units. Okay. You never want to forget the units because that's the most important part. Not just the solution, but also the interpretation. So since 36 hours is 3 half-lives, the amount goes from 80 to 40 to 20 to 10. Okay. So 36 hours is 3 half-lives. Okay. That's how you interpret this. 36 hours is 3 half-lives, right? Okay, because a half-life would be 12. So a half of a half of a half. So it'll go from 80 to 40 to 20, and then to 10 grams, which is how we got that, right? Because half of 80 is 40, half of 40 is 20, half of 20 is 10, and then you can about a guess in another 12 more hours, it's going to be where? 5, right? 5 grams. Okay, let's continue. Okay, example number 3. We have to solve for time. An investment grows 5,000 to 9,000 at 7% annual growth. Solve 9,000 equals 5,000 multiplied by, has a multiplier of 1.07 raised to the power of t. So thankfully, this is already in the form that we want, right? So we have 9,000 equals 5,000 parentheses 1.07 raised to the power of t. Now we need to solve this for t using logarithms. So this is in the form that we would want to see if we were still doing decay in this way. But I'm going to show you how to do it using logarithms. Okay, so here we are not solving for the final amount, right? We already know the final amount. The final amount is 9,000. We're solving for this. We're solving for the exponent. So we want to start by isolating the exponential expression, right? So we have our problem, and what we're going to do is the first thing we're going to divide by 5,000. So when we divide by 5,000, we'll end up with this side because it simplifies to 1. And then the other side, notice the variable t is the exponent, right? So we we are going to use logarithms. And so what we're going to do is take the natural log of both sides. Now, I do need to simplify this. So 9,000 or 5,000 goes into 9,000, and it's going to be 1.8. Okay. So now that this is simplified, we can essentially take the log of both sides. So we have the natural log of 1.8 equals the natural log of 1.07 power of t. Now, this is very important because, I'm essentially going to put those parentheses. We can use the power property, right? The power property says that I can bring down t, right? Bring down t. And so that's going to be ln 1.8 equals t ln parentheses 1.07. Okay. In doing that, we can take the natural log of 1.07 and divide it to both sides to get t. So I'm just going to bring that up here. So the natural log of 1.8 equals t. Matter of fact, I'll just do it like this. 1.07. Okay, then I'm going to divide both sides by the natural log of 7. Okay. And then this will tell us what t is. I'm just going to switch it around. So we know that this is going to be reduced to 1. So I'm just switching it over here. So I'm going to bring this over to the other side. So it's going to be, it's going to look like uh, the natural log of 1.08 divided by the natural log of 1.07. So the same thing, I just switched it around. And then once you do this, you're going to get an approximation in the calculator. And the approximation is going to give you t is approximately 8.688. Okay. So it takes around, we'll say 8.7 years, right, for the investment to go from 5,000 to 9,000, right, at 7% growth. 8.7 years is a long time to get from 5 to 9,000. It doesn't seem like, and I'll just keep in mind This is if you're not putting any money in this account. This is just the 7% annual growth on a money account that you're not investing in. You've already invested capital, but you're not putting any money in it every month. So it's just going to compound at the 7% rate, and then it's going to get to 9,000 in 8.7 years. Okay. That's what that means. That's the interpretation. Okay. Let's continue. Um, Example number 4. So find the balance when 2,400 is invested at 5.5% compound continuously for 10 years using A equals P times E raised to the power of R times T. So the principal is 2,400, right? So we have P, the principal is $2,400. Okay. And then the rate, or the R, is equal to 5.5%. And remember, 5.5% can be written as a decimal if we move it twice. Let's just do that here. 5.52. Okay, so that'd be the new percent, 0.055. And then we have T equaling 10 years. T to 10 years. And then all we have to do is substitute. So A equals 2,400, right? A sub O, and then multiplied by E. That's going to be A sub O times E. And then that's raised to the power of R, which is 0.055 multiplied by 10. Okay, those two multiply each other. And then we can multiply the exponent first. So that would be 2,400 times E raised to the power of 0.55, right? So you just simply shift it over. From there, we're going to get an approximation, right? So A is approximately 4,159.81. Okay. So the answer is, in dollars, $4,159.81. So after 10 years, the balance will be that much. Okay. And again, this is investing 5.5. This is with a principal amount that is invested and a 5.5 continuous compounding for 10 years. So this is not you putting money in the account. This is just how much it would be if it compounded at that rate without being continuously invested in on your part. All right. And then the common mistake, capstone, is a student writes 1.06 as 6%. Explain the difference between the rate and the growth in this case. All right. So the mistake is simply confusing the rate with the growth factor, because the rate is the percentage change written as a decimal. So if it was 6%, then R would be equal to 0.06, right? The growth factor is what we multiply by each time period. So for growth, the factor is 1 plus R, right? That is the growth factor. So for 6% growth, that would be 1 plus 0.06, right? And that would be essentially 1.06, right? Now, the 1 represents the original 100%, and then the 0.06 represents the additional 6%. So the rate, 0.06, the growth factor is 1.06. So 1.06 does not mean 6%. It means 106% of the previous amount. So again, Okay, very important. Okay, so just for a final review, remember when you're dealing with exponential and logarithm applications, these are your best friends. Okay, and again, thank you for watching.